back to my YouTube channel. So we are going to be looking at another question on Sturm problem. So we have a question in front of us that says consider the Sturm equation to be this, and we are given a condition that says x is greater than 0 or equal to 0, and between less than is between 0 and let's just put it this way: x is between 0 and pi is 90 degrees. So let's say x is between 0 and 90 degrees. So now we are given the condition, and we say for every value of x when x is equal to 0, y is equal to 0, which is right here. And we're also given for when y prime, when x is a function, when x is equal to pi, y prime is also equal to 0. In this case, unlike our first example, we are given y prime. So now let's solve. So like I said before we solve a Sturm equation, or what a Sturm equation means, is asking us to do. We are going to be looking for the eigenfunction and the eigenvalues. The eigenvalue, and the eigenvalue is when we are the values we get when we are not obtaining a trivial solution. Then the function we get after that is the eigenfunction. So now let's proceed. Solution. So like I said, we are going to be looking at three cases. We are going to be looking at when lambda is greater than 0, less than 0, and equal to 0. So let's consider when lambda is less than 0. Let's call it 1. So when lambda is less than 0, so now let's bring our Sturm equation to the plain ground. So this is my Sturm equation, and I said when lambda is less than 0, right? When lambda is less than 0, I'm just simply multiplying it by minus 1. If I just multiply lambda by negative, it means lambda is less than 0, right? So let me just put it here. So this is y prime minus negative y equals 0. Right. So then we assume this is a second order equation, right? Which is actually a second order equation. So now we all know that for second order equation, the solution of this form, the square y, the x square minus n square y is equal to, which is equal to 0. The solution of this second order equation is given as y is equal to a cos n, a cos nx plus b sine nx. So this is the solution of this form. So now if you take a look at this also, they actually alike. This is my second order derivative right here, and this is also my second order derivative right here. This is my lambda, which is I can make it to an equivalent of n square, and this is my y, and this is my y, and that's also from here. Now comparing this and this, my n is equal to what? Comparing this and this, I have my lambda is equal to n square, right? Then which means my n is equal to square root of lambda. So instead of me going to all this stress, I just substitute this right here. So my equation is given as, now let's call this a and b, c1 and c2, which is actually the same thing. We are just changing the form of the constants. We're just changing the alphabet. So let's consider our solution to be c1 cos nx plus c2 sine nx. Then I said my n is square root of lambda, right? So this is c1 cos square root of lambda x, right, plus c2 sine square root of lambda x. So like I said, this is the solution to my Sturm equation. So now we are not done yet. We are going to be looking for the values that we can, the value of lambda that will not give us a trivial solution. Remember I said a trivial solution is when y is equal to 0. So now let's check if this gives us a trivial solution. So now looking at the equation in front of us, now how do we check if this gives us a trivial solution? Now we use our boundary condition. Now our boundary condition we're given to be this, right? We're saying we're given to be x is between 0 and pi, And for the function of x, right, given x between 0 and pi, and for the function of x, y, x for nx is equal to 0, y is equal to 0, and when x is equal to prime, when it's equals to pi, y prime is also, y prime of pi is equal to 0. So the first thing we're going to do now is to substitute when x is equal to 0 in our solution. So when x is equal to 0 here, so what can give us 0? So when I put 0 here, let me just substitute it. So we have c1 cos root lambda 0 plus c2 sine root lambda 0. So I know that 0 times root lambda is 0, right? And cos 0 is 1. Then 0 times root lambda here is also 0, but sine 0 is 0. So this gives me 0, this gives me 1, then y is equal to c1. And we know from the boundary condition that when y as a function of x is 0, y is also equal to 0. So if y is 0, c1 is equal to 0. So from the boundary condition, when x is 0, y is also 0. So if y is 0, c is 0. So that's that. So we have gotten our first c1. Now, you have gotten c1 to be equal to 0. Now, if you can remember, I said from the first problem we solved, if c1 and c2 are both 0, the equation is a trivial solution. Why? Because if c1 is 0, this is 0. So if c2 is also 0, c is also 0. If c2 is 0, this is also 0, and which makes y equals to 0. And if y is equal to 0, we have a trivial solution. Then we can use the case. But if c1 is 0 and c2 is not 0, is not a trivial solution. Or if c1 is 0 and or if c1 is not 0 and c2 is 0, is not a trivial solution. So that's that. So let's check for the second boundary condition, which we are given to be y prime of pi is equal to 0. So now let's differentiate my y, right? What I have to do now is to differentiate my y and substitute when x is equal to pi, and easy as that. So we know that from this first process, we know that c1 is equal to 0, right? If I decide to write my original equation, this is c1 cos root pi x plus c2 sine root pi x. Now you know that c1 is equal to 0, right? So I can just remove this, take this off the face of the earth. So this is y is equal to c2 sine x. So this is the formula I'll be working with, right? So now what I have to do now is to just differentiate my y. So this is y prime. Let me use of x, because this is a function of x. So this is a constant, right? So I'm just going to be differentiating my sine right here, right? So differentiating sine, what will you have? If you differentiate sine x, you have cos x. The same thing with sine x, cos x. If I differentiate sine x, I have cos x. The same thing if I differentiate sine x, I also have cos x. So this is a constant, so differentiating sine x. Now remember, this is, I assume this is like a function of function. So differentiating sine x, this comes to the back. This is root lambda. Then sine x, which is cos x of lambda x. This is just like saying differentiate sine 2x, right? If I differentiate sine 2x, this is 2 cos 2x, right? 2 comes to the back. So that's exactly what I did there. So then we have y prime of x to be equal to c2 root lambda cos root lambda x. So like I said, we are going to substitute for our second boundary condition when x is equal to pi, right? So substituting when x is equal to pi, so you have c2 root lambda cos root lambda times pi, right? So what do we have here? So we're having pi times root lambda times pi. We're having pi times root lambda cos of everything, right? Then this is root lambda times c2. So now equal to 0. So if m is equal to 0, no, actually, if you make m is equal to 0, cos this is equal to 1. So if you make this to be 1, can we get c2 to be equal to 0 here? First, we need to check if this second figure, or if this second term right here is 0. for any possible value it can be. If it's 0 for any possible value it can be, then we have no choice but to make this 0. What we're trying to look for is that we're trying to look for, since they said y prime of this is equal to 0, right? So technically all this is equal to 0. So for this to be equal to 0, either C2 it will make it 0, or this second term right here will make it 0, right? So we now want to assume that let C2 not be equal to 0, because if C2 is 0, it give us a trivial solution. So now let's work with this second term. So we're going to look for if this second term, if it has any hope of not being equal to 0. So now let's check the second term. Now we have cosh root lambda pi. So now let me represent cosh as its function of series. You know that taking root lambda times pi to be m. So this is cosh m, right? Taking this to be m. So we know that cosh m is equal to exponential m. Writing the general form for cosh m, which is exponential m plus minus exponential minus m divided by 2. It's plus. So this is general form for cosh m. So now we're going to look for, so what can make cosh m now to be equal to 0? What can we substitute as m that will make cosh to be equal to 0? So if you can try on, there is actually nothing you can do, only if you make m itself to be equal. This cannot be equal to 0. Then we have no choice but to make C2 to be equal to 0. So we have C2 is equal to 0. So C2 is the only factor that can make this to be equal to 0. Then we can say that this is a trivial solution. So y equals C1 cosh lambda x plus C2 shine lambda x is 0, and which makes it a trivial solution. So we're going to do the same case for when lambda is equal to 0. So in my case 2, when lambda is equal to 0. So given our Sturm-Liouville equation of this, when lambda is equal to 0, what do we have? We have this, which is equal to 0, right? Then we can also assume this to be second order differential equation. So when we solve this, let's assume when we solve this using auxiliary equation, this is m squared, right? And this is equal to 0. So square root of both sides, square root of both sides. So we're having plus or minus square root of 0. We're having 0 and 0. So remember, when we're having two equal roots in a second order differential equation, or generally our standard solution is usually y is equal to c1 exponential m1x plus c2 exponential m2x. So when we're having two equal solution, we'll be having c1 exponential m1x plus x c2 exponential m2x, right? So we substitute our m1, this is m1 and this is m2. So m1 substituted here, this is c1 exponential 0 is 1. So this is c1 plus x. Substitute here also, exponential 0 is also 1. So we have c2. So we have this. So my equation, I can fully write it out to be. So we have this equation in front of us. So what do we do next now? So we're going to apply our boundary conditions, right? So our boundary conditions were given as x is between 0 and pi, and when substitute when x is equal to 0, y is equal to 0, and for y prime, substituting when x goes to pi, we have also 0. So now let's substitute in our equation. So this is y is equal to c1 plus when x is equal to 0, so this is 0, and which makes y is equal to c1, and which makes c1 to be equal to 0 because of this condition. So let's apply for our second boundary condition. C1 is equal to 0. Our second boundary condition, we have C. Since C1 is equal to 0, no need to rewrite it into the equation. So you can just put xc2, right? So when x is equal to pi, Okay, when I say, sorry, our second boundary condition says when y prime is a function of pi. So now let's differentiate this. So this is y prime, right? Is function of x equals, so this is x, right? Differentiating this is just c2, right? So since there are no function of x and they said y prime is equal to 0, so this is equal to 0, right? So we have c1 and c2 to be equal to 0. That means c1 plus xc2 is equal to 0, and this makes it a trivial solution. So we can use that. So for final cases, our final case when lambda is greater than 0. So right now, Sturm-Liouville equation, which is y double prime plus lambda y equals 0, right? So now when lambda is equal to 0, we know lambda for any number to be greater, when lambda is greater than 0, so for any number to be greater than 0, it has to be positive. So we can just leave it like this. So applying our method of solving second order differential equation, like using auxiliary method. So this is m squared plus lambda equals 0. So taking lambda to the other side, this is m. Remember, m is the root of m is just the value for this quadratic equation we have here. So this m squared is equals minus lambda, right? So if in case you don't understand how I'm expressing all this, I advise you to go and watch my videos on second order differential equation, how you can actually solve them, and how they take all these forms. So square rooting both sides. So this is m plus or minus square root of minus lambda. So we can actually use complex number. Remember, this can also be expressed as plus or minus square root times minus square root of minus 1 times minus lambda. No, these are actually equal. So our complex number says square root of minus 1 is represented by this let's just represent by this complex number. Let's call it j. So my m, right, is equal to plus or minus, bringing this here, so this is j lambda. So now the differential, the general solution for this form, d square y dx square plus n square y equals to 0, is the general solution for this type of differential equation. Is y is equal to c1 cos nx plus c2 sin nx. So we don't actually need to go through all those steps, since this equation matches perfectly to my general Sturm-Liouville equation here. I just need to substitute for n. So comparing the two equations, lambda is equal to n square, right? Square root in both sides. My n is equal to square root of lambda. That's that. So, but yeah, that's that. So what do we do right here? We just need to substitute for lambda. So since this stuff right here, we don't actually need to go through all this stress of writing this and this. We can just actually take value from here. So let's proceed. So the general solution of this form, we don't actually need to go through all this stress, but we actually went through all this stress. So the general solution for this form of second order differential equation is this. So comparing this to this, my n is root lambda, right? So substituting it back into my equation, this is y is equals to c1 cos square root lambda x plus c2 sin root lambda x. So now we solve. So we apply our boundary condition. That's what I mean. So applying our boundary condition when x is this and this, and for when x is equal to 0, y is 0, and y prime of x of pi is also equal to 0. So these are my boundary condition. So let's solve. So substituting when x is equal to 0, so this is c1 cos lambda times 0 plus c2 sin lambda times 0. And we know that sine 0 times this is 0, and sine 0 is also is just 0, and 0 times this is 0, but cos 0 is 1. So this is c as a function of 0 is c1, right? It's equal to c1, and since they said it's also equal to 0, so which means this is equal to 0 and c1 is equal to 0. So that's that. So now let's since c1 is equal to 0, we can just cancel this out and just write only this. So this is y is equal to c2 sine root lambda x. So we apply our second boundary condition by differentiating this, right? Because this is y prime, right? So if this is not actually y prime, you don't actually need to differentiate it, just substitute your value of x. So differentiating this, it is y prime as a function of x. So applying this is root lambda cos root lambda x. That's that. So since they said it's going to be a function of pi, since they said x is equal to pi, so this is we have something like this, root lambda cos root lambda and pi, right? So now, since we've tried two different cases and they gave us trivial solution, that means we expect this to give us our eigenvalues. So that means we cannot expect c to be equal to 0 again. So we can actually make this to be equal to 0, or meaning that we should expect this second term here to be equal to 0. So now how do we do that? So now let's check. So which factor that which since we are not expecting c2 to be equal, because now they said this is equal to 0, right? And meaning that either c2 or this right here will make this to be equal to 0. But since we are not expecting it from c2, we are to expect this. We are to expect it from our second term. So since this is a constant, it doesn't play here, so we can just take this cos here, right? So now, meaning that we are expecting our cos lambda times pi to be equal to 0. So now how can we check if this actually can give us 0 for different set of values, right? We are not actually looking for only one value. Okay, we are looking for set of values that can make this cos to be equal to 0. So now let's bring out this cos right here. So this is root pi times lambda, right? So let's equate it to be 0 because we're expecting it to be equal to 0. So let's divide through by cos, then this is root lambda times pi equals cos inverse of 0. So cos inverse of 0 is 90. That's the only value that can make cos to be equal to 0. That's not actually the only value that can make cos to be 0, but technically speaking, when you punch your calculator, you just have 90 degrees. So 90 degrees is expressed as pi over 2. So this is root lambda times pi, right? So just work with me. So pi can cancel pi, so lambda is equals to 1 over 2, right? So we've gotten lambda to be 1 over 2. Let's just take it back into our stuff, which was c1 lambda cos square root of lambda pi, right? And we got lambda to be we got square root of lambda to be 1 over 2, right? So and when I put it here, which means I'm having cos 1 over 2 pi, right? So now, since we're having one value of lambda, which is 1 over 2, that will make cos 0, because when I replace lambda with 1 over 2, I have pi over 2, and pi over 2 is 90, and which makes it 0. So now let's check for other values of series of 1 over 2 that can actually make this cos to be equal to 0. So if I say, okay, since lambda is 1 over 2, right? Let's try for 3 over 2, right? Now let me try for 3 over 2. When I put, let me try for 3 over 2, so that meaning that when I put 3 over 2 here, let's see if it will give us 0. So checking for cos 3 over 2 pi, right? Which means checking for cos 3 times 90, and punching your calculator gives me 0. Wow, nice. So we have two values now that can make cos to be equal to 0. So cos doesn't have any excuse now for being 0, because it's trying to make an excuse by telling c1 c2 to be equal to 0, right? But now we have actually gotten two evidence that it actually needs to be 0. So now let's check for that one. Okay, let's check when if 5 over 2. Now in this case, you just have to be using trial and error, punching your calculator to see values that can make cos to be equal to 0 from the first value, right? So let's check 5 over 2. Let's check cos 5 over 2 pi. So this is cos 5 times 90, which gives me, punching your calculator, 0. Nice. So, but if you notice something, we're having 1, 3, 5, meaning that we are having odd number series, right? So what is the general form for odd numbers? General form for odd numbers is 2n minus 1, right? Lambda to be equal, our first value of lambda was 1 over 2, right? And the remaining series were 3 over 2, 5 over 2. I'm sure if you do for 7 over 2, 2, you also have the same question. So now let's write, what is the general form for odd number series for the numerator? This is 2n minus 1, and since we're having constant value of 2, 2, 2, 2, 2, we can just represent it like, right? So if you notice, we're having 1, 3, 1, 3, 5, 7 as odd numbers, so we can represent it as the standard form for odd numbers, which is this. And since we're having a constant value at the denominator, we can just represent it as 2. So this right here, when I take the square of all this, they're actually my eigenvalues, right? If I take the square of all this, which makes this lambda, remember lambda itself is my eigenvalue, not root lambda. So if I take the root of this, I have my eigenvalues, right? But since it's giving me an infinite series, let me just represent it as the standard or the general form. So root lambda was equal to 2n minus 1 over 2, right? Then square rooting both sides, square rooting both sides. Then I have my lambda to be equal to 2n minus 1 over 2 all squared. So this right here is my eigenvalue for when n is equal to 0, 1, 2, 3, and so on and so forth. So I've gotten my eigenvalue. So what next is for us to determine our eigenfunction. So how do we get our eigenfunction? Now we go back to our general our solution we got after we got c1 to be equal to 0. So this is the solution we got after we got c1 to be equal to 0. This is the solution we got. So we go back to this solution. So this is the solution we are looking for. So we we input our value of lambda. So let's do that. So the solution we got after we made c1 to be equal to 0 was y c2 sine square root of lambda x, right? So imputing my values of lambda. So since I'm having root lambda in this, I have c2, this is sine 2n minus 1 over 2 times x. So this right here is my eigenfunction. Remember, these is supposed to be functions, because when I decide to put when n is equal to 0, I have a different function. When n equals to 1, I have a different function. When n equals to 2, I have a different function. The same thing goes for the eigenvalue. It's supposed to be eigenvalues. When I put n equal to 0, I have a different value. 1, a different value. 2, different value, and so on and so forth. So these are the two key things we have been doing all those stressful work to come about. So thank you guys for watching, and please do so well to subscribe. Peace.